Okay, so we're going to do section 3.2, number 37. This is a little bit of a long one. It says, consider the graph of the function f of x equals negative x squared plus 5. And let's graph that function. Well, we still have the one from the previous problem, so we'll just reset it. And we will look at negative x squared plus 5. Enter. Oh, I have scales. Let us standard zoom. There we go. Okay, that's good. And they tell us, find an equation for the secant line joining the points. So find a secant line joining negative 1, comma 4 and 2, comma 1. Why'd they pick these particular points? Well, the x values are probably arbitrary. They're just something different from one another. But negative 1, comma 4 is a point on the function, and 2, comma 1 is also a point on the function, being points here and here. So the secant line, if we want to find an equation for it, first we can find its slope. M equals, we'll do 1 minus 4 over 2 minus a negative 1, 2 minus a negative 1. That's y2 minus y1 over x2 minus x1. So that is going to give me negative 3 over 3, which is negative 1. So my slope is negative 1. I could use one of two things. I can say y minus one of my two y values is going to be equal m times x minus one of my two x values. Let's use, I don't know, the first one or the second one. Maybe the second one. Maybe that looks a little easier. So this gives me x minus x1. So this gives me y, the equation of my tangent line, is going to be equal to, my secant line, y minus 1 equals negative 1 times x minus 2. Distribute this negative 1, I get negative x plus 2. Add the 1 to both sides. I get the y is equal to negative x plus 3. So let's graph that and see if that is our secant line that joins those 2 points. Negative x plus 3. Right, and it looks pretty good so far because I cross right at negative 1 comma 4 and right at 2 comma 1. So here's my secant line, and that's good. So let's return to this, and I did the secant line, so that is part A of this problem. Part B of the problem says use the mean value theorem to determine a point C in the interval negative 1 comma 2 such that the tangent line C is parallel to the secant line. So there is going to be some value that the tangent that runs through the function is going to be parallel to this secant line. And that is guaranteed by the mean value theorem, provided that on the interval that I am considering, my function is both continuous and differentiable. It is both continuous and differentiable. F prime at x equals negative 2x plus 0, right? That's the derivative of my function here. We can see that this function is a polynomial. All polynomials are continuous, and I can find its first derivative for any value of x. So it is both continuous and it is differentiable on the entire real line and not just between a and b, being the values of these secant lines on this interval. So that's good. So we can use the mean value theorem then. The mean value theorem guarantees that there will be at least one tangent line that will be equal to this secant line for some value x in an interval from -1 to +2. So let's try and find that. So that is part B. We know that our derivative, we just calculated up there, is equal to -2x, right? And we want to find a value such that it equals the value of the slope of the secant line. So is there going to be some c equal to -2c that will be equal to -1? So this is from here. This is the slope of the secant line. And this is found by saying f of a minus, or excuse me, f of b minus f of a over b minus a. And the mean value theorem says that as long as on the interval from a to b we are continuous, and on the open interval from a to b we are differentiable, then there will be some value such that my derivative, some value c in a to b, that my derivative will be equal to the slope of the secant line. And that value is -2c equals -1, found by solving this equation, and that equation is at c equals 1/2. And 1/2 is indeed in the interval from -1 to +2. So let's try it out. Let's probably the next part will say find the equation of the tangent line through C. Okay, so here is my C value. The value of the function at 1/2 will be equal to -1/2 quantity squared plus 5, which will be equal to -1/4 plus 5, which will be equal to, let's see, 20 minus 1 over 4, which equals 19 over 4, approximately, right? So then if I, the value of this has to be -1, right there, because I just solved it, right? So my slope is, so I'm looking for an equation of a line that goes through the point 1/2, comma 19 over 4 with slope equal to -1. So I can kind of use the same process that I did before. Y minus y1 equals m times x minus x1. So then y will be equal to, let's see, y will be equal to -1 times x minus 1/2 plus this y1. I'm just adding it to both sides here, a little prematurely maybe, but 19 over 4. Distribute that, so I get -x plus 1/2 plus 19 over 4. We bravely saunter on with our adding of fractions in a very non-approximative way, if that is even a word. Alright, so 2 over 4 plus 19 over 4, so that is going to be -x plus 21 over 4. Oof, I hope that works. Let's see. If I put in -x plus 21 over 4, I should get out a tangent line. It's definitely going to be the same slope as this, so it's going to be parallel. And hopefully 21 over 4 will make it pass right through the function at a value equal to what was it? 1/2. Right? So there it is. And that looks just about right. So here, this line is parallel to this line. It is tangent to the function at some point in the interval between -1 and +2. So that's good. And we've already done part D. It says, then use a graphing utility to graph f, the secant line, and the tangent line. And we did that. Here is the secant line. Here is the tangent line. The tangent line passing through this value of c, comma, f of c, guaranteed by the mean value theorem. So that was number 37.